Hey everyone, welcome to Chemistry 1111. Dr. Carroll here. This is lecture 3 in Unit 8, and today's lecture is all going to be about solids. And in our textbook, that is beginning on page 383. And let me just go to the slides here to get sort of an idea. We're going to understand amorphous and crystalline solids at the molecular level. Amorphous means without form, really, that's what it means, but in our case it's random arrangements. It's not direct arrangements in some repeated lattice or set of unit cells as we see in crystalline solids. So glass can be amorphous, quartz can be crystalline, and so here's our definitions. Amorphous means no ordered structure to the particles of the solid, no well-defined faces, angles, or shape. Often are mixtures of molecules which do not stack together well, or often large flexible molecules. Examples include glass and rubber. So glass shatters in all sorts of different ways, and that's because it's amorphous. Whereas crystalline solids, the atoms, molecules, or ions packed together in an ordered arrangement. They have flat surfaces, unique angles between the faces, and a unique three-dimensional shape. Examples of crystalline solids include diamonds and quartz crystals. So there you have it. We'll spend most of the time focusing on crystalline solids. Let me go back to the textbook here. Did I choose a pen yet? I don't know. Let's see. There we go. So the solids, they may be crystalline or amorphous. They're vibrating about preferred locations. Regular repeating patterns in a crystalline solid. If it's not regular repeating, then it's amorphous. Precious gemstones like rubies, sapphires, emeralds are highly valued crystals of rare and richly colored minerals. A solid having an irregular arrangement is classified as amorphous. Now, whether it's crystalline or amorphous can be dictated by how the crystal, how the solid's prepared. Silicon dioxide, if can be quartz, which is crystalline, and with 1710 value for its melting point degrees Celsius. So if you have molten SiO2 and slowly cool it, you'll get crystalline quartz. But if you cool it really quick, you'll get amorphous glass. Okay, so the chemical engineering is important here. How the rate at which we cool something can cause different arrangements of the atoms. They're both three-dimensional networks, but the two-dimensional representations show the differences between crystalline and amorphous. So here we see on the left here, this is crystalline, nice repeated patterns. Then here, the patterns aren't repeated so much, so that's amorphous. Okay, so in a crystal, you have parallel faces and edges. They intersect at characteristic angles. Into smaller pieces, fragmentation occurs along the edges. Small crystals have the same angles as larger crystals, and a crystal has a higher degree of symmetry. So here's some nice cool gemstones, vanadinites, quartz, and stibnite. Okay, stibnite happens a bit after midnight. And then there's Batman. There's always Batman. So let's look at the crystal lattice in the unit cell. Here's an Escher drawing showing a repeated pattern. So that repeated pattern can be thought of as the unit cell. You have a vast array of atoms, molecules, ions arranged in some regular repeating pattern. We looked at lattice energy, we looked in crystal lattice. So we place a point at the center of each species contained in the crystal. The crystal lattice of the pattern forms throughout the crystal by these points. And that reflects the symmetry. It repeats exactly. Every crystal has one smallest unit from which the entire pattern can be assembled, and that's known as the unit cell. So it's now we are talking about biology here. We aren't talking about cell phones. We're talking about crystalline substances which have a unit cell. Okay, a repeating unit. That unit cell faces can be squares, rectangles, parallelograms. We'll focus mostly on squares and rectangles. Okay, so let's start with that, with the cubic crystals. And do my slides help out here? There's a unit cell, is the smallest unit from which the entire cell can be assembled. So if I look just at a portion of it, I see here 1 cubic cell, and there'd be 1 atom in the cubic cell because you have 8 corners, and that would each is 1/8, so 1/8 times 8 is 1, so there'd be 1 atom per unit cell in what's called the simple cubic cell structure. Actually, let's just use the mini text. Okay. So this one here is called simple cubic lattice, also called simple cubic, SC, sometimes called primitive unit cell. So you just see all these atoms stacked on top of each other, and the repeating centers gives you the unit cell. When 8 atoms form a cube, there is a cavity at the center of the cube. Cavity means nothing there. The cavity is not large enough to hold an additional atom, but moving the 8 corner atoms slightly away from each other does allow the structure to accommodate another atom. Okay, so now that was the simple cubic. Now if I can get 1 atom inside here, I get what's called the body-centered cubic, or BCC. Each atom in a body-centered cubic lattice is at the center of a cube and contacts 8 neighboring atoms. In other words, every atom in the structure can be viewed as the center atom of one body-centered cube, or has a corner atom in an alternate cube. So the unit cell of a body-centered cube contains a total of 1 plus 8 times an eighth, 2 atoms. Okay, so simple cubic contains 1 atom, body-centered cubic contains 2, and iron in figure 18, 8.24 shows this. So here's iron, and so we have the atoms at the corner, and then we have a full atom in the center. So that is what's known as body-centered cubic. Okay, and then we can start stacking the unit cells to make the iron. Now the face-centered cubic is pretty cool. In this arrangement, you have 8 atoms at the corners, shared with 8 other unit cells, but you also have an atom at each face. Okay, and each of those atoms is just sharing with one other atom. So there's 6 of those, right? There's 6 faces, each sharing with one other. So that makes it 6 times half is 3, plus the ones on the corner. So there's 4 atoms in what's called a face-centered cubic. Face-centered cubic is also called cubic closest packed. Those are both names for them. So that's face-centered cubic, and you see nice pictures on page 385 about that. So let's see. Alkali metals form crystals with body-centered, face-centered cubic. There's lots of examples of those. And you want me to find one? Face-centered cubic. Silver. Silver is an example of that. So let's try some calculations about these. And I'm going to need my periodic table to help me. I'm also going to need to turn on the lights. It looks like it's storming outside, so everything just got hard to see. And I need a calculator. So here we go. Let's see how all this works. But before that, let me make a little summary of what we have going on here with these 3. So I'll do that in Paint. So I can have a simple cubic. Start again. Simple cubic, body-centered cubic, or face-centered cubic. And the number of atoms. The book doesn't do a table of this, so you might be good for you to write that down. 1, 2, 4. And then we also have the length of a side, so the length of a side of the unit cell. For a simple cubic, well, you just have one atom stuck up against the other, so it's just 2 times R. Body-centered cubic turns out to be 2.309 times R. And I'll let you do the trigonometry to show that. Face-centered cubic is 2.828 times R. Okay. There's also something called the coordination number, but I don't think we're going to need that at this moment. Coordination number is the number of nearest neighbors. For face-centered cubic, it's 12. For body-centered cubic, it's 8. And for simple cubic, I think it's 6. But I can double check that. But that is the coordination number, which I don't think we use for anything. Okay. So another thing we're going to be using is the reminder that density is mass over volume. That helps in these kinds of calculations. So let's go back to the text, mini text here. Calculate the mass of a single unit cell of polonium which crystallizes in a simple cubic structure. Simple cubic structures are not that common for metals, for anything really, but polonium does. So we know that there is 1 atom per unit cell. The molar mass of polonium is 209 grams per mole. So the mass of the unit cell then is, what's 1 atom? 1 atom, let's see, mass. If I know that the molar mass is the grams over the moles. So the grams, 209 grams per mole divided by 6.02. That'll be 4 mole. Okay, let's yeah, I know that, but that's not going to help me here. Let's start again. I got 209 grams in a mole, but I want grams in 1 atom. Well, the mole is 6.02 by 10 to the 23 atoms. So the mass is 3.47 by 10 to the minus 22 grams. Yeah, the stuff there, what I shouldn't have written that in. So 209 grams. Here's an easier way. We got 1 atom, right? 1 atom. If I had 6.02 by 10 to the 23 atoms, it would be 209 grams, but I don't. I just have 1 atom, so it's 209 divided by 6.02 by 10 to the 23, which gives me how many grams per 1 atom. So 3.47 by 10 to the minus 22. Is that all they wanted me to do, was to get the mass? Really? Okay, yeah, that's all they want you to do. Okay, so exercise 8.5, calculate the mass of a single unit cell of silver, which crystallizes in a face-centered cubic. So there you get the molar mass of silver, which I'm looking at a hard copy periodic table, 107.87. 107.87, but I want it for just 1, so 6.02 by 10 to the 23, and then I want to multiply all that by face-centered cubic, so there's 4. So 4 times 107.87 divided by 6.02 by 10 to the 23, 7.2 by 10 to the minus 22 grams. Right, because there's 4 atoms in there. Calculate the mass of a single unit cell of sodium metal. Well, body-centered cubic, so I'm going to multiply by 2. So 2 times something over 6.02 by 10 to the 23. Sodium molar mass is 22.9. Lighting got really bad here. 22.99 something. Let's just round it to 23. So 46 divided by 6.02 by 10 to the 23. 7.6 by 10 to the minus 23 grams. Okay, so those are the masses of single unit cells for a few metals, and that's going to help us with some of these other things with density. And one thing that helps in terms of units is a centimeter is 1 by 10 to the 10th picometers. Pico is 10 to the minus 12, right? So a meter is 1 by 10 to the minus 12 picometers. So if I multiply both sides by 100, and I got that wrong, didn't I? Start again. 1 picometer is 1 by 10 to the minus 12 meters. So if I divide both sides by 10 to the minus 12, I get a meter is 10 to the 12th picometers. That's a meter, 1 by 10 to the 12 picometers. And now if I divide by 100, a hundredth of a meter is a centimeter, divide by 100, so 1 centimeter is 1 by 10 to the 10 picometers. Why am I even talking about this? Because in density for solids, picometers are used a lot and cubic centimeters are used a lot. So it's nice to show and then to memorize that 1 centimeter is 1 by 10 to the 10th picometer. It'll just help with a few things. So let's calculate the density. Density rho, units of grams per cubic centimeter for solids, right? If it was a liquid, we could write it as grams per milliliter, but it's solid. Now, I got the silver mass already, so that's why it's going to help me here. If the edge length is 407 picometers. Okay, so we already know the mass from our previous question for silver, 7.2 by 10 to the minus 20 seconds. So we got the numerator, and then we got to get the denominator. So to calculate the volume of the unit cell, we need only the edge length, and then we cube it, right? It tells me the edge length. I'm not given atomic radii here. I'm just told the edge length is 407 picometers for this face-centered cube. So I just cube that, and I get 6.74 by 10 to the minus 23 cubic centimeters. Okay, if I want to use this thing I was talking about to get cubic centimeters earlier, 407 picometers, 1 centimeter is 1 by 10 to the 10 picometers. This is 2. I'm going to change the, I'm going to make it thinner there. Okay, so I get 407 divided by 1 by 10 to the minus 10. Get some value, and then I want to cube that, and I get 6.7 by 10 to the minus 23 cubic centimeters. The mass we got before, so then the density, mass over volume, 10.6 grams per cubic centimeter. Usually, everyday solids have a density of like 1 to 100 grams per cubic centimeters. 100 is pretty extreme. Anyways, so there's my mass per volume. So that's how you do questions like this. You have to know the identity of the metal. You have to know whether it's body-centered cubic, simple cubic, or face-centered cubic. And you have to know the either radii or length of the edge of the cube. And you take it from there. Note that the density of a large piece of silver metal is the same as this 1 unit cell, since metals are in effect a large assembly of unit cells. So density is an intensive property. It doesn't depend on how much of something you have. And a density of 10.6 grams per cubic centimeter is reasonable for a metal. So let's try the practice exercise. Iron metal, which we got before the maths, right? We did that. Sometimes these practice exercises and examples work with each other. And I'm looking here and I say, no, we didn't do iron, we did sodium. Okay, so that's fine. Calculate the density of iron metal, which crystallizes in a body-centered cubic structure having unit edge length of 287 picometers. Okay, so I'm going to get the length 287 picometers, and I want to get that into centimeters. So what was that magical thing I said? I said a centimeter is 10 to the 10th picometers. 1 centimeter is 1 by 10 to the 10th picometer. So it becomes 287 by 10 to the minus 10 centimeters. So the volume is length cubed. 287 divided by 1 by 10 to the 10th. 2.87 by 10 to the minus 8th. Fine, right? I'm going to cube it. And I get 2.36 by 10 to the minus 23. That's cubic centimeters. Now the mass, well, what was iron here? Body-centered qubits. So it's going to be 2. There's 2 atoms. And 6.02 by 10 to the 23 goes into the denominator. And what the heck is iron? I gotta look it up here. This is 55. Boy, this 55.85. My eyes are going on me. So 2 times 55.85 divided by 6.02 by 10 to 23 is 1.86 by 10 to the minus 22. Grams. So the density is mass over volume. So 1.86 by 10 to the minus 22nd grams over 2.36 by 10 to the minus 23 cubic centimeters. .86 grams per cubic centimeter. See, the answer at the back of the book has 7.83, so it depends where you round it. Okay, let's do a few more. I like these ones, I think they're fun. Calculate the radius of a palladium atom, giving the density is 12.02 grams per cubic centimeter and that it's face-centered cubic. Okay, so the mass of a palladium atom because it's face-centered cubic, times the molar mass of palladium, which turns out to be 106.4, divided by Avogadro's number, because you want it for the mass of an atom. No, sorry, not the mass of an atom. Careful. You want the mass of the unit cell, not the atom. The mass of the atom would be a quarter of this, but there's 4 of them. So there's the mass. The volume is length cubed, but I'm given the density here, so rho is m over v, so cross multiply, m is rho v, so v is m over rho, and I got the mass of the unit cell. I'm given the density, so the grams cancel, and you get the volume, and from there I can take the cube root of both sides to get the length, right? The length is the cube root, 3.89 by 10 to the minus 8th centimeters. And then I memorized before, you'd actually be given this. Let's give, where was it? 2.828 R. L is 2.828 R. So R is L over 2.828. So you get 1.38 by 10 to the minus 8 centimeters, and you can convert that into picometers if you want, because atomic radii are commonly expressed in picometers. So there's a few steps here, but this is a classic kind of question. If you want, there's the proof using Pythagorean theorem of how I got that. The R is L divided by 2.828. Okay. Let's try this one here. Chromium. Okay, so I got to get the molar mass of chromium. $51.996, so just 52. Okay, so chromium is 52 grams per mole, body center cubic, so 2 atoms in a unit cell, 2 times 52 divided by 6.02 by 10 to the 23. That's the mass of the unit cell. And I got the volume, let's see. Rho is m over v, so v is m over rho. So there's my m divided by my rho, 7.14, and that's going to equal my length cubed. So then I can get the length, and then I can get r. So let's work that out. 2 times 52 divided by 6.02 by 10 to the 23, all that divided by 7.14. So that's the volume, which is length cubed. So then I'm going to raise to the 0.3333 power, and I get 2.89 by 10 to the minus 8th. And that's the length. And that equals 2.828 R. So R is 2.89 by 10 to the minus 8th divided by 2.828. You can keep it in roots if you want. 2.89 by 10 to the 8th minus divided by 2.828. You get 1.02 by 10 to the minus 8 centimeters, or 102 picometers. I don't have that answer written down. Practice exercise 8.7. I hope I'm right. Shall we take a look? Practice exercise 8.7. Now we're going somewhere else now. You can double check while I'm looking for it here.